from Raleigh, China. First off, please allow me to give a quick introduction about our journal. EcoMat is a flagship journal published by Raleigh in collaboration with the Hong Kong Polytechnic University. It is a gold open access journal, and we aim to publish on a wide variety of topics from different disciplines that focusing on cutting-edge materials for green energy and the environment. The scope of EcoMat is intentionally broad, including energy harvesting, storage and conversion, batteries and supercapacitors, energy systems and networks, fuel cells, water and air pollution control, carbon capture, etc. The articles can be immediately opened once published with a rapid average publication speed. EcoMat has already published 13 issues online so far since it was launched in 2019, and the article publication charges are still waived until this year's end. Our ambition is to make a mark in material science and its adjacent fields of a high academic impact. Here, I would also like to introduce a bit about our dedicated editorial team. Our editor-in-chief is Professor Zijian Zheng from Hong Kong Polytechnic University. We have 4 associate editors who are Professor Songbin Yuan from Northwestern University, Professor Song In Sok from UNST, Professor Qiang Zhang from Tsinghua University, and Professor Huijun Zhao from Griffith University. We also have Dr. Sami Lo as our managing editor based in Hong Kong. EcoMat has already been indexed by SCIE, DOAJ, and COS, etc. before. We will receive our first impact factor in this summer. Thank you, the dedicated editorial team. Thank you, our global board members, and all of the authors, reviewers, and readers. Thank you, everyone, so much for your continuous kind support. Last but not least, we welcome you to follow our social media accounts. Please scan the codes here and follow our news on WeChat, LinkedIn, Facebook, and Twitter. Also looking forward to your next submissions. Currently, we accept research articles, review articles, and research highlights. Now, I'd like to hand over to EIC to start our today's webinar officially. Also, please do not be shy to post your questions in the chat box during our meeting. Many thanks.
Thank you, Daisy. So good morning, good afternoon, good evening, everyone. Sami, can you go back 2 slides? Right, so I'm Zijian Zheng, and Daisy just gave a very nice introduction of EcoMat. The EcoMat webinar series began in about 2 years ago, actually, when the pandemic just started. And since then, we've been organizing this webinar series pretty much every month. So every month, we'll give one focus topic given by 2 or 3 international leading scientists in the field. And so today, we will have a fuel cell and water electrolyzers topic. And as editor-in-chief, I will welcome you to enjoy our webinar. Please also subscribe to EcoMat journal since it's open access right now and it's free for everybody. I welcome you to submit your best work in energy and environment-related research to EcoMat. Well, we'll have our first impact factor this year for sure, and the prediction according to the data is going to be over 10, the impact factor. So we look for high-end original research or high-quality review or perspective for articles. You are most welcome to submit your research outcomes to us. Okay, so without further ado, I would like to hand over the chair to our associate editor, Professor Zhang Qiang from Tsinghua University. Qiang, I think the time is yours to chair this webinar. Thank you.
Yeah, hello, Zijian. This is Qiang from Tsinghua University. Good morning, Europe. Good afternoon, Asia, and good evening for American. So let's start our EcoMat webinar series in March 2022. So we have two speakers today. The first one is Professor Minhua Shao. Let me introduce Professor Shao briefly. Professor Minhua Shao earned his bachelor degree and master's degree in chemistry from Xiamen University at 1999 and 2002, and got his PhD degree in material science and engineering from the State University of New York at Stony Brook at 2006. He received the Superman Silver Young Investigator Award from the ECS Energy Technology Division. Now he is a full professor in Department of Chemical and Biological Engineering and director of Energy Institute of the Hong Kong University of Science and Technology. His research is mainly focused on electrocatalysis, fuel cells, and advanced batteries. And also, if I remember correctly, Minhua also associate editor of Journal of Electrochemical Society. So please join me to welcome Minhua.
All right, thank you very much for John's kind of introduction. Let me share my windows. Okay, can everyone see my slides?
Sure.
All right, good.
I can see the slide here very clearly.
All right, thank you. So first of all, thank the chair's kind of introduction and also Professor Zijian Zhen's kind of invitation. So today I will give a talk on the fuel cell electric catalysis. Okay, so basically we try to develop the catalyst not only has high activity but also durability. So that's the key point for the fuel cell real applications. So first I'll give a brief introduction, then I will focus on three systems. The first is a culture-based catalyst for the oxygen reduction reaction, that basically catalyze the reaction of fuel cell. And then I'll talk about a new type of catalyst we call hybrid. So basically there's a non-precious metal plus a precious metal. So two components for oxygen reduction. And last is briefly talking about this hydrogen oxidation. So even though the reaction kinetics of hydrogen oxidation is not a big issue in the proton exchange membrane-based fuel cell, but in alkaline-based fuel cell, the hydrogen oxidation is actually quite slow. So we're actually talking about this, the system using ruthenium to modify platinum, and then we talk about the mechanism of this activity enhancement. All right. So fuel cell is actually not a new technology. Actually, has been there for several decades. Okay, and for the proton exchange membrane fuel cell, the biggest application, of course, will be the electric vehicles. So the cost for the fuel cell system, if you look at this chart since 2006, all right, so it has been reduced significantly. Of course, now we're talking about the system cost about 40 to 50 US dollar per kilowatt. Our ultimate target is about 30. So it's very close, but still a long way to go. Okay? So in addition to the...
Sorry, interruption, Minhua. Are you playing the slides?
Yes, yes. Yeah, I am playing. So you can see the slides playing.
I can't.
Right,
so I'm not sure how about the others, the moderator.
No, we can't see it. It's
you still.
I think you need to full screen your slides first. It's not in full screen mode.
Let's see. Is that full screen now?
No, not from my side.
Mr. Shah, I think you have to share the full screen window instead of the PowerPoint window. If you can try sharing the screen again.
Okay, so let me try. Okay.
Maybe you unshare and share again.
Yeah.
Sometimes it happens.
So the entire screen, right? Or the window, because there's a couple of things.
You can choose the full screen window or just the entire screen. Both will also
Okay, so maybe an entire screen sharing. So what do you see now?
Yep, it's good.
full screen now.
Okay, okay. Sorry about that. Because we used to use Zoom, right? So not familiar with this team. Okay. Anyway, so in addition to the manufacturing costs, actually the material costs actually play a significant role in the cost reduction. So if you look at this chart on the right, you see that the catalyst actually almost is 50% of the total material cost. And this is not a surprise because we're using platinum-based materials, and we know platinum is one of the most expensive material. Okay. So for the cathode reaction, so there's the oxygen reduction. Now the Fox recently is on the anode. Okay, so the benchmark is platinum supported on carbon black. So the mass activity at 0.9 volt is about 0.2 amp per milligram for platinum. Okay, by annoying platinum with some transition metals like cobalt, nickel, iron, right, or copper, so the mass activity can be enhanced, and the reason is due to the ligand and the strain effect. Okay, so those transition metals are smaller, so it creates a compressive stream. Recently, if you're just using this anode, the activity enhancement is typically limited to like 2 to 4 times. But if you can play the morphology, okay, and the other nanostructure, we can find that the mass activity, so that's the red, the green column, activity can be enhanced by almost 70 times. So this is the platinum nanowire, and this is the platinum nickel molybdenum octahedron. So basically all are 1-1 phases. You can see that the activity can be enhanced significantly. All right. So now the problem here is that even the mass activity that you measured in the nucleus cell, for example, the rotation disk electrode, okay, most of the time you cannot be realized in the real fuel cell, and that's the big issue. Okay. So I basically summarize the issues of recently developed highly active platinum anode in the structure. The first is there no durability. Okay, so the activity that you made in nuclear cell is basically very at a room temperature, and basically the condition is much I think it's less critical than in the real fuel cell. Okay. And then it's also the synthesis is very complicated. Okay, so this is not good for the mass production of a real catalyst. And the third is the lack of the real fuel cell testing data. So this is give you an example. So this is called the Nano Frame, right? So developed by Professor Peidong Yang and Stankovic, right? So you can see you synthesize the polyhydro first, the platinum nickel, and then you do the deannoying to remove most of this. The elements inside of the polyhydro, and then you basically form this Nano Frame and do the annealing to form this very nice material. But if you look at the activity that you measured from this RDE, right? So the Nano Frame have about 20 times of mass activity over a benchmark platinum. Right? But if you put this in the fuel cell, you can see that even when during the conditioning, that mass activity continues to decrease. Okay. And then even at the high current density area, the performance is much lower than the benchmark platinum. So basically, if you develop a highly active material, but it cannot be realized in fuel cell, then it will have a big gap, right, for the real application. Another area for the fuel cell cathode development is non-precious metal. So it has been a long time ago, the people found that for the some of the transition metal coordinated with nitrogen and carbon has some activity for oxygen reduction, but this molecule is actually not stable. So recently, they find that if we started with the carbon black support, and then we introduce some of the iron or nitrogen precursor and do the heat treatment. So basically, you modify the carbon support. I have a thin layer of this carbon and the nitrogen and the iron stuff. Okay, so this is actually quite active for the oxygen reduction. And at that time, you see some of the nanoparticles, and basically we could not find out which is the real active size, right? And later on, if you have, it's a very advanced microscopy, we can find that in those empty area, actually there are some single atoms, so the iron coordinate with nitrogen and carbon. So that's possibly will be the real active size. Okay. So another way of synthesize the non-precious metal, actually back to Dognay in 2011, we found that I can use this ZIF or MOF, okay, starting with those as basically is a template. And then we can dope with a small amount of iron, and then you do heat treatment, okay? So basically, iron will stay in this morph, and the morph itself will become a carbon black. Basically, it's a nanoparticle, okay? So basically, you can find that the method, the performance of this material is actually much better than previously synthesized non-precious metal, and it's very close to platinum. But if you look at the stability, okay, so he tested both, two material, okay, both of them actually did not show good stability. So non-precious metal, but if you cannot solve this durability issue, it cannot be used in the real fuel cell. So next, I'll talk about our approach. Okay, so in the precious metal side, we basically started with a core shell structure, because the fundamental, rationale here is that because the reaction is occur on the surface. Okay, so if we can limit the platinum actually on the surface, and inside the nanoparticle, we can using other metals. Okay, hopefully it can be cheaper. Right. So basically, you have the high utilization of platinum. Right. So with this monolayer concept, we when I was still a student, we developed this kind of thing. But it's very difficult to deposit the platinum monolayer, a well-controlled monolayer. So we started with called the under potential deposition process with the intermediate step. So what we do is here we started with a material like a palladium, and then we deposit a copper monolayer into it using under potential deposition. So under potential deposition is cannot occur on any of the pairs system. It only occur on some of the noble metals. Okay. So the deposition of the copper will occur on the potential higher on the potential thermodynamically predicted. And then with this monolayer, we can replace the copper by put this system in the platinum solution. So this will be 1-to-1 ratio exchange. Ideally, you have one monolayer of copper will be replaced by one monolayer of platinum, right? So you can see that we tried this system with palladium nanoparticle, okay? And in the copper solution, we can see we start at a high potential and then scan the potential to negative. You can see before it reaches the bulk deposition of copper, this is about 0.37 volt. You can see some of these small peaks. So this current peak associated with under potential deposition of copper. So before the bulk deposition of copper, you have one layer of the copper deposited on the palladium surface. Okay. But now the further challenge about this core shell structure is the mass production. How do you actually synthesize this monolayer structure in a gram scale, in kilogram scale even, right? And the second is that you have to further reduction, the further reduction of the noble metals inside of this metal, the core. Okay, for example, palladium. How do you remove most of them? Okay, so this we have done a lot of stuff. So first, we're talking about the mass production. So if we want to produce a lot of the core shell, basically you need to design a reactor, okay, so that it can give you at least a gram of material to be tested in the fuel cell. And we found that it's not easy. Okay, when you scale up, we found that instead of forming a platinum monolayer, most of the time you form this platinum cluster instead. Okay, so can we have a physical block to prevent the deposition of platinum, further deposition of platinum? Okay, so basically, if we have something that absorbs on platinum surface or copper surface, then the only place that the platinum can go is the item that the position of the copper item left. Okay, so you can basically use this as a template to guide the deposition of the platinum item. So this is actually has been confirmed by our in situ X-ray diffraction. So basically, you know, the material, core material that we synthesize, you have only one platinum monolayer and supported on platinum nanoparticles, right? So if you do this X-ray diffraction experiments in a regular atmosphere, for example, helium or air, you only see this one single peak, because palladium and platinum, you know, their lattice constant is very similar. So basically, you cannot distinguish in X-ray diffraction. But if you do this in hydrogen, because palladium is a good hydrogen storage material, so it absorbs a lot of hydrogen, so that will have a lattice expansion, right? So it will cause the X-ray diffraction peak shift to a low angle for palladium. But if you have you know, large clusters of platinum, right, on platinum nanoparticle, you will see this shoulder here. This shoulder will not leave, okay, from the original place. So this we confirm that in our mass production, we have this problem, formation of platinum large clusters and then nanoparticles, right? So this is quite a useful technique to assess the quality of our core shell catalyst. So what we did here is we put some citric acid in the deposition solution. You can see that first we did some experiments on the single crystal palladium 111 deposition. Okay, so that's the platinum deposition on palladium 111. So that's the black curve. That's the regular normal curve. Okay, so you start the deposition and then is a regular peak. Okay, but if you have some citric acid in it, you will see that the deposition starts at the same potential, but it actually inhibited at a certain potential, and then start to the deposition start to continue again. All right, so that means that the platinum that deposited on the surface actually have some inhibition, okay, for the further deposition of platinum, and because of the citric acid, so there's a specific absorption on the platinum surface. And we did this on the nanoparticle, so similar phenomena also observed, but of course this is not a single crystal, so you will see this kind of inhibition not as clear as on the single crystal. Okay, so this is basically we found that the citric acid plays a role in the deposition, you know, kinetics. Okay, and we did this on the RBE cube and also mass production batch. So what I hear is that we measure the open circuit potential change of the electrode. Okay, because the electrode initially covered by copper monolayer, so the open potential is low. After you replace with platinum, the open potential will go up to reach the platinum open circuit potential. Okay, so you can monitor this change of open circuit. Okay, so without citric acid, the increase very fast on the RDE, 25 seconds, the whole process is done. Okay, and if you add 200 millimole of citric acid, you can see the blue line. So this process is significantly delayed. Okay, so that means the citric acid actually reduced the reaction rate. Okay, and we can do this on a grand scale. The similar thing happened. Okay, so without citric acid, this process occur finished in 200 seconds. With citric acid, it's basically you know, delayed until like 500 seconds. Okay, so we also did some simulation. So basically, to simulate this displacement reaction, okay, copper is replaced by platinum cation, and with the citric acid, how the citric acid actually play a role in the changes the reaction rate. Okay, so this is okay. Let me. So this one is actually without citric acid, and you can see how this platinum layer deposited on this palladium surface without citric acid. Okay, so it will probably take time. Right. So the second one is that with citric acid, you can see that citric acid actually prevent the formation of large holes. Okay, this is with citric acid. Without citric acid, sorry, this is probably take too long. So, but you can see the final result. Okay, so this without citric acid, you form these big holes. Okay, so pinholes without the platinum, Okay, and with citric acid, actually these pinholes are much smaller, and the platinum shell is much uniform. Okay. So then we did the XRD again in the hydrogen. We didn't see any shoulder anymore. Okay, so that means this platinum shell is more uniform, and the mass activity of the core shell we can see now reach 0.9 about m per milligram of platinum. Without the citric acid, is only 0.4. Okay, so the mass activity also improved significantly. And we did this fuel cell performance. Okay, compared with platinum benchmark. Okay, in both air and oxygen. So the solid line is in oxygen and the dashed line is in air. So this data actually published in 2016. At that time, has not been optimized, but is at least clearly showing that there's this improvement, okay, over the benchmark of platinum. Okay, so that's the first time that we demonstrated that the core shell, okay, not only in the RDE testing, but also in the real fuel cell, actually we have better performance than the pure platinum. Another phenomenon that we are quite interested in is the stability of the core shell. The first thing is the thermal stability, because we are talking about the core shell is actually monolayer scale. Okay, so it's possible that the palladium and the platinum actually can mix it together on the surface, and then form the alloy on the surface. Okay, so we wanted to understand this phenomenon. So at what temperature this mixture already can occur? Because this is very important when we prepare the ink. Okay, before we put in this catalyst on the in the fuel cell, we typically using different mixing method, and that can create a high local temperature. Right. So we did this study on the in situ TM at a different temperature. We can see that at 250 Celsius, we started to see some of the particle migrate closely, but there's no growing. Okay, so particles still separate. They are not growing to one single particle. Okay, and then we do the stem yields correlation on the same single particle, so same particle. Okay, before heat treatment and after treatment, we can see that after heat treatment, actually there's a mixing of the palladium and the platinum. Okay, so initially you have the very sharp peaks, so that means the core shell is very clear. But after heat treatment, 250 degrees C, you already see this the mixture. So we also did this using the in situ XRD. We can see that in hydrogen, okay, starting at about 150 Celsius, we started to see this peak shifting. Okay, it's not clear as that as a synthesized material. And if you look at the 300 Celsius, okay, most of the material, the peak is not shifting. And this is reasonable because if you form an alloy shell, okay, instead of pure platinum shell, the hydrogen is not easy to diffuse in this palladium core. Okay, so causing this peak shifting not as clear as this single, the core shell structure. So basically, at a high temperature, you already form this kind of alloy surface. Okay, and this temperature we define is about 150 to 200 degrees C is already started. So when you prepare the ink, you have to make sure that the temperature, local temperature, cannot be that high. Otherwise, your core shell structure is damaged, will be damaged. Okay, and we also use the CO stripping to confirm this kind of structure change, right? So the black line is a synthesized core shell, and the dashed line is basically on pure palladium. So you can see that as a synthesized core shell catalyst, the CO stripping peak is actually much lower than the pure palladium. But after the heat treatment is actually shifted to a closer to the palladium. Okay, so that means the structure of the surface composition is already changed from the pure platinum to a mixture of palladium and platinum. And this activity associated, the activity change also very clear. Okay, after annealing, the mass activity will dropped. Okay, for the 300 treatment sample, the activity dropped by 30%, so a significant activity drop. Okay. Next, we are going to talk about this further reduction of this palladium inside of the core. So what we did here is that, after you synthesize this core shell catalyst, we're now using a chemical method to remove some of the palladium in the core. Okay, so there are two purposes. First purpose, of course, we try to remove some of the noble metal inside the core, palladium, right, to reduce the cost. Second is that after you remove some of the palladium in the core, actually, because your particle size will shrink. Okay, so resulting in this redistribution of the platinum on the surface. So that means your platinum layer probably will be thicker than the original one. Okay, so original probably 1 to 2 layer. So after the heat, the post-treatment, your thickness of platinum grows to 2 to 3 layer, right? So that it can further protect your core shell structure. So we try a different method, okay, for this post-treatment. Okay, so this is the first is the initial one, okay, platinum on palladium, and then we can using the bubbled air inside of solution to dissolve palladium, or you bubble oxygen to dissolve palladium, or we can further increase this the concentration of the iron inside of solution. So further, because the iron is a highly oxidative species, so can oxidize the palladium. Okay, so you can see that with this different kind of conditions, the palladium to platinum iron ratio, okay, decreases, right? So with air is a milder, dissolution condition. The palladium to platinum iron ratio changes from 3 to 2.3. And if you add oxygen instead of air, it further reduced to about 1.9. If you add the iron chloride, it decreases to 1.5. Right? So basically, you can remove a lot of the palladium inside the core. Okay, and the surface active area comparison also confirms the increase of the platinum shell thickness. Okay, so initially we are talking about 150 square meter per gram of platinum. Okay, after post-treatment, okay, for the last one we decreased about to 110. Okay, so that means some of the platinum is actually buried in the sublayers. Okay, so resulting in this surface area reduction. All right, so now we also put this catalyst in the fuel cell, and then we tested the performance. We can see that both the core shell with dealloying or without dealloying core shell are much better than platinum-based catalyst. Okay, but the most important thing here is that not only the activity, but also the durability. So we tested the durability of this dealloying this core shell. We can see that by comparing with benchmark platinum, right? So the red one is our core shell. The black one is the platinum. Okay, the solid before durability testing, and the dashed is after durability testing using the square wave cycling. So about 30,000 square wave cycles. Okay, 80 degrees C, 100% RH. You can see that the performance decay for a core shell is actually much lower than the platinum. Okay, so if we're talking about the mass activity at 0.9 volt, for the platinum dropped about 55%, and for the core shell is only 38%, and for the surface area drop for the platinum is about 60%, and the core shell is about 50%. Okay, so both are much lower than the platinum-based one. So it's actually we confirm that with this kind of approach, we can significantly improve the performance and the durability. Okay, and this is a post-analysis. This is the beginning of test of core shell. You can see this is a uniform distribution of the platinum shell. After this 30,000 of cycling, we still have this core shell, but you can see that the thickness of the shell increases. Okay, so that means you still can move some of the palladium in the fuel cell testing, but with this durability testing, the platinum grow big, thicker and thicker, and further protect the shell. Right, so that's the final structure of the core shell structure still there. So next, we'll talk about the hybrid catalyst. Okay, so this is a combination of the non-precious metal. That's the iron, nitrogen, carbon as support, and then you basically have some noble metal nanoparticle on it. So basically, this idea is coming from this the paper from Dr. Liu Dijia. Okay, so basically they did this cobalt nitrogen carbon support as the matrix, and then supported some platinum cobalt nanoparticle on it. So they found that the particle actually the catalyst show good performance. Okay, but the problem is that after this durability cycling, 30,000 cycles, the durability actually decreases significantly. Okay, so we try to do is a different approach. So we're using this iron-based non-precious metal and platinum iron, this nanoparticles. So even though the iron-based non-precious metal has worse durability than cobalt-based nitrogen carbon catalyst, but surprisingly, the hybrid catalyst based on iron actually has much better durability. So I talk about a little bit more. Okay. So first, we actually design some of the synthesis methods of the iron nitrogen carbon. So using this ZIF8. Okay. So we partially dope with iron, and then do heat treatment. You got this iron nitrogen carbon support, and then we mix some of this platinum salt. Okay. Do the boil mini. Okay. So you actually incorporate some of the platinum in this carbon, and then do the heat treatment in argon again. So you got the platinum and iron nitrogen carbon mixture. Okay, so this is the correlation of the iron nitrogen carbon. So basically, with an iron doping. Okay, so you can see that even though the morphology changes significantly, but more or less the ZIF structure is still there. If you do this STEM, you find that this is not a very smooth surface. Okay, so this is a rough surface. So this is basically the carbon, and you dope some iron nitrogen into it. Okay, so this is good because it can create a larger surface area for further platinum supporting. And this is the further correlation of the single iron atom. Okay, so you can see that the iron distance can range from about 0.3 nanometer to 0.4 nanometer. So the 0.4 nanometer means that there are nitrogen coordination, okay, with different the two different iron, and with 0.3 nanometer, that means the two iron actually does not have nitrogen coordination. Okay, so another go details. So here is some of the TN images showing that the nanoparticles of platinum iron, and also in addition to the very small nanoparticles, is about 2 nanometer. Okay, very very small, and then you also have these single items. Okay, so these are the a lot of single items, and that's basically majority of single items are iron. And we did some of the testing, and you can see that in the RDE testing, the iron, nitrogen, and the platinum doped iron nitrogen. Basically, the activity, there's no big activity difference. But surprisingly, you can see that if we do the platinum cycling after 70,000 cycles, the activity of the platinum iron nitrogen does not show any of the activity decay. Okay, so there's no difference in the half-wave potential. But for the iron nitrogen, it's only 10,000 or 16 millivolt, and for platinum, 40,000 already 11 millivolt. Okay, and this is some of the post correlation after the platinum cycling. Okay, so after 70,000 cycles, up to 1 volt, you can see the particles still there, right? But if you go up to 1.1 volt, the majority of the particles are gone, but the single item is still there. You still see a lot of single items. Okay, so that is the the dissolution mechanism for the nanoparticles and the single items are totally different. Okay, so we also did some fuel cell testing. You can see that the platinum iron nitrogen actually has better durability than iron nitrogen. Okay, but this is improvement is very limited. Okay, so later we design another method to synthesize this platinum iron nitrogen carbon. So we actually basically use ammonia treatment. Okay, so now we also see that there are a lot of single items, and then there are also nanoparticles, and these nanoparticles, the majority of them has the ordered structure. Okay, so it's also very small, 2 to 3 nanometer. And in these single items, we actually using the yields. We found that some of them actually the iron, single atom. You can see the blue line is a very weak iron, and the red is actually platinum single atom because we don't see this iron peak. Okay, so you have different type of single atoms, okay, and then combined with the small nanoparticles. And this is also further characterized by the X-ray diffraction to showing that this ordered platinum iron structure. Okay, and we also did some of the chemical correlation. You can see that in the RDE, this RDE, the activity of the platinum iron nitrogen is actually have about 150 millivolts of shift. Okay, so that's significant. And when we're talking about the loading of platinum is only 1 to 2 weight percentage, and iron is about 2 to 3 weight percentage, very low metal loading. Okay, and then fuel cell testing, you can see that now the black curve is for our hybrid colors. No, the black is the platinum benchmark, and then the red one is our platinum iron nitrogen. Okay, so you can see the performance is already very close to the benchmark platinum, but the platinum loading is much lower. Right? For platinum is 0.1 milligram per square centimeter. For the hybrid is only 0.15. Okay, so it's 7 times lower. Okay, but the most interesting thing is that after 100,000 cycles, the hybrid catalyst does not show any decay. For the platinum, only after 30,000, you can see the decay is already significant. Okay, the mass activity already dropped by 50% after 30,000, and for the iron nitrogen, after 30,000, also power density also dropped significantly. Okay, and for the hybrid, if you keep the same potential, the current density does not show any decay. Okay, after 200 hours, we can do this much longer, but we actually stopped the testing. Okay, so this is the first time that we demonstrated that not only the mass activity but also the durability can be significantly improved for this non-precious metal. Okay, so lastly is basically you're showing this kind of post analysis. Okay, so after the 100,000 cycles, what kind of structure that left? So you can see that for the nanoparticles, it's become a coiled structure. So you have a pretty pure platinum shell, okay, and then you still have the platinum alloy. And for the larger particles, 5 nanometer about, you see this form this percolated structure. So that means there are some porous structure, right? So for the larger particles, but the larger particles are very small. The majority are still small particles, and you still see these single items left. Okay, both platinum and iron. Okay, so that means this composition are still there. All right. So last, I only maybe spend 2 minutes talking about the last. Okay, so the platinum is actually very good for actually hydrogen oxidation and also hydrogen evolution, but in the alkaline, the activity is much lower. Okay, so recently they found that using some of the transition metal like nickel or ruthenium, put on the surface, the activity can be enhanced. Okay, but the mechanism is not clear. So the widely accepted by functional mechanism is that the platinum is active site for hydrogen bonding, and then foreign metal like ruthenium is it provides also facility. So that means absorb this oxygen based. Okay, so promote this kind of hydrogen oxidation or hydrogen evolution reaction. But we found that is not actually true, because what we did here is that we put the ruthenium on platinum surface, okay, by changing basically the coverage, and we can monitor the platinum hydrogen bonding and the ruthenium hydrogen bonding, a different coverage of ruthenium, right? So we found that here is a pure platinum, and then with different deposition time, we found that the platinum hydrogen bonding. Okay, we also see the ruthenium hydrogen bonding, and this is basically we can calculate the coverage of ruthenium hydrogen. We can see that the platinum hydrogen does not change at all the location, right, the wavelength. That means that the platinum and ruthenium has no anode effect. Okay, and the ruthenium is actually also very active sites for hydrogen bonding. Not only to provide to absorb oxygen. Okay. Then we also measure this hydrogen oxidation reaction kinetics. Okay, also HER, using the bottle warmer to fitting to the exchange current. And we found that this exchange current actually have a linear relationship with the ruthenium coverage. So that means the ruthenium is actually the active site instead of a role of the providing this adsorption site for oxygen. Okay, so this is not the bifunctional mechanism. Instead, the ruthenium is the real active site in this system. Okay, so we also did some of the theoretical calculation, but I'm not an expert in this theoretical simulation, so I'm not going to talk about it. Okay, all right. So with that, I will not give the conclusion because we're talking about the different stuff. Okay, so I would like to thank all the funding agencies and also the group members who performed this start. Okay, thank you, and welcome any questions.
Professor Shao, thank you very much for your wonderful talk. I have several questions from the audience of the webinar. So the first one is, why choose palladium as the core of the catalyst?
Right. So, as I supposed to say that, as I mentioned, that it's not easy to find a good pair of this UPD phenomenon, because under pressure deposition can only occur on some of the noble metals surface, like palladium, ruthenium, gold, platinum, and this is the first. And the second is that based on the DFT calculation, the palladium core actually have a electronic or called a ligand effect and the strain effect on the platinum shell. So that effect actually can improve the activity of platinum. So not only just the reduction of platinum item, but also improving this specific activity of platinum items. So that's the two reasons that we choose this palladium as a core.
Yeah, thank you. So I see another question about the catalysis before and after reaction. Are there any physical and chemical differences between your catalyst before and after fuel cell test? I noticed that cell performance has somewhat deteriorated. Do you have any comments on preventing the catalyst deactivation?
Yeah, definitely there are a lot of changes in the catalyst, including both the structure and also the composition, right? The first change is there are some dissolution of palladium. Okay, we're talking about different systems, but just using Corsair as an example. Okay, so there's a dissolution of the palladium and also platinum. So that's you see this kind of particle size change and also the shell thickness change. Okay, and the second is that there's a particle growth because there's called austral ripping. And so this is basically the dissolution and the redeposition. So basically that it can give you a particle growth, right? So there will be a lot of change in the catalyst. And for the hybrid one, we also see a lot of change. Okay, so you can see that as synthesized, this nanoparticles of platinum iron, after cycling, it becomes to a coherent structure, and some of them become a porous structure, right? And it's possible that some of these single items will be dissolved. Okay, even though we did not see too many of this, but certainly there will be some change. Okay, yeah.
Yeah, I see there are another 2 minutes for this talk, so I have the questions about, does the ruthenium have a strong or weak absorption for hydrogen? Does the ruthenium exist as a single atom?
Yeah, so ruthenium is actually not a single atom in our system. It's basically we deposit the ruthenium as a cluster. Okay, it's not a single item. And in the full layer of coverage, of course, you have 1 or 2 layers of ruthenium on platinum surface. Okay, so it's a bulk. It's not a single item. And we found that the ruthenium is actually the binding on the hydrogen itself. Ruthenium itself is too weak. So if you can increase the binding energy of hydrogen on ruthenium, you can improve the HOR or HER performance of ruthenium. Yes.
Okay, due to the time limitation, I have to stop the discussion for Professor Minhua Shao's talk, but I'm sure you can find more research progress and details in his publication. So Professor Minhua, thank you very much for your Wonderful talk.
All right, thank you all. Yes.
Yeah. Then, according to the schedule, we shift to the second speaker of our webinar. Our second webinar was Professor Zhao Chuan. He is a professor at the School of Chemistry at the University of New South Wales, Australia. And he is the head of UNSW Nanoelectrochemistry Lab of more than 30 researchers. He also held a professional future fellowship from Australia Research Council. He currently is the chair of the Royal Australia Chemical Institute Electrochemistry Division and elected as the Fellow of Royal Society of Chemistry, Fellow of RACI, and Fellow of Royal Society of New South Wales. Professor Zhao received his PhD in 2002 with an Excellence Award from Northwest University, and then he completed postdoctoral research at the University of Oldenburg and Monash University. He started his independent research career as a lecturer at UNSW in October 2010, and he was promoted to full professor. Please join me to welcome Professor Zhao.
Thank you, John. Can I share my screen?
Sure, please. I can hear your voice.
Okay. There we go.
You can find the share button or the third one.
For some reason I couldn't see the slides. Just a moment.
Okay, no worry, no worry. And according to my experience, Professor Zhao have carried out a very excellent work in the field of electrocatalysis, and you can find his publication in this field. He has strong background in electrocatalysis, and also his current talk for today is advancing electrocatalysis for water electrolysis. And if you read Professor Zhao's publication, you will find a lot of important research progress. Please, Professor Zhao, I already see your slide.
All right, thank you, John, and thanks for the kind invitation. And so today I will sort of introduce some of our progress in electrocatalysis for water electrolysis. So I'll quickly start introducing the background of the research. So the climate change, everyone can feel it. The challenge is simply huge and urgent. And to combat the climate change, one of the key approach is to use more and more renewable energy. And this is a map of the solar energy irradiation around the world. What we can immediately notice that is that the distribution of the solar energy or any type of renewable energy, they are uneven around the world. Okay, for example, in Australia, we get enough solar irradiation. People have done the calculation that, for example, if you open the solar farm in Western Australia, 250 by 250 kilometer, using the current commercial solar cell technology with around 20% efficiency, it can generate 25 petawatt-hour electricity per year. That's the total electricity the whole world needs for a year. So the problem is, how could we sort of transport electricity generated in that location to the rest of the world? To do that, we need a carrier. And hydrogen is considered to be one of the best candidates for doing that. So this comes to the concept of the so-called hydrogen economy. And so in the hydrogen economy, basically, we could generate hydrogen from the renewable energy, using renewable energy, and in a device in the water electrolyzer, and generate hydrogen. And that's the hydrogen production section. And the next section is hydrogen storage. And then also we can then use the hydrogen on different location, on different time. That's the hydrogen utilization. So overall, these three sort of main technology forms the so-called hydrogen economy. And this basically also summarized the research in my group. So we basically do research around these three sectors. So one of the main research theme in my lab is on water electrolysis to make hydrogen. And please talk about the hydrogen economy, we're talking about green hydrogen. Okay, the hydrogen production without CO2 emission, and also the energy for hydrogen production has to be renewable. And then we also do a bit of work on CO2, on the hydrogen storage. Hydrogen is difficult to store and transport. So we are looking for other carriers, like we do the hydrogenation of CO2 to make hydrocarbon or carbohydrate, to use them as a carrier. And also we can do that in the nitrogen reduction electrolyzer and producing ammonia as a hydrogen carrier. And also hydrogen itself is reactive, molecular hydrogen particularly, but the other form of hydrogen, which is proton, is actually very stable. So looking for material which can actually store proton, and then we can make, for example, a battery as well. And then the hydrogen fuel cell, and where we're also sort of trying to develop non-precious metal-based catalysts, particularly for the OR reactions. So I want to emphasize that the hydrogen is not only just for fuel cell, it's actually very important products or chemical stock material for chemical industry. For example, in the current industry making ammonia, we use Haber-Bosch methods, which also use need hydrogen as a precursor. So for all this sort of CO2 hydrogen conversion devices, there are two key devices. One is water electrolyzer, the other one is fuel cell, and Professor Shaw gave excellent introduction about the fuel cell. So I'll be talking about the electrolyzers. So everyone's familiar with this, the polarization curve of the two process of the water electrolysis. On the anode side, we have OER, and the cathode side, we have HER. So water electrolysis is actually a well-established technology. It has been there for more than 100 years. But why it can't be used for the green hydrogen production? It's not a mainstream hydrogen production technology yet. So the main problem is the cost. So we know actually for OER, anodic reaction, actually there's a significant overpotential for the OER side due to the sluggish kinetics of the reaction. So one of the key issues actually is the high energy consumption. So that is the efficiency of your catalyst. So when we have we need a good catalyst to reduce the electricity consumed for the electrolysis. For that, we need a highly active catalyst. And the other contributor is actually from the high cost of material. I mean, for the OER, for example, the transition metal is actually noble metal actually is the benchmark catalyst, for example, ruthenium, iridium for OER, and platinum for HER. And then to reduce the material cost, and we need to develop non-precious metal-based catalyst. And the other issue is actually so normally we talk about test our catalyst. We are working in the sort of this kinetically controlled zone. But in the reality, when you really work in the device, you actually often will step into the mass transport confused area. So where we can see a strong gas evolution, often you will see the very noise signal, but also often you will notice that your catalyst is not that stable actually. So all these issues are actually current major hurdles for the electrolysis to produce hydrogen at a low cost. I'm just talking about OER this side, but same issue almost happened on the HER side. We need a high activity catalyst with low cost material with excellent stability. So there are three sort of mainstream water electrolysis technology. Alkaline water electrolyzer, which is basically two electrode in two chamber of a stack, and then separated by so-called separator, and this is basically to separate gas from mixing. And then another one is the proton exchange membrane water electrolyzer, which has a very similar structure as the fuel cell, and where we use the proton exchange membrane to separate, have a membrane electrode assembly. It's a zero gap, very compact structure, and it offers lots of advantages. For example, very high current density, fast response. And these are the two sort of main water electrolysis technology currently being used. And there's also recent study on the anion exchange membrane water electrolyzer, which basically combine advantage of the alkaline electrolyzer as a PEM electrolyzer. The good advantage there is it can use the non-precious metal as a catalyst in the electrolyzer. So I'll be mostly talking about alkaline water electrolyzer today, but no matter which electrolyzer technology, they actually share some of the common issues here, summarized in this figure. So normally when we do the water electrolysis test, we working on a steady state standard condition in the lab, but in reality, the operation condition is very different. So we need to actually mimic those operation conditions to test our catalyst. And we also need a stable catalyst, active stable catalyst. And gas bubble is a big problem. So water splitting, both anode and cathode, they are gas evolving reactions. So gas bubble generally a big problem. I'll come back to that in a minute. And membrane, as is case for every electrochemical device, membrane is actually a crucial component. Any development in membrane will be improved technology significantly. And support is important, particularly the support for the catalyst, the interaction between them directly decide the stability of the catalyst in device. And impurity, most of the research we do in using the ultra pure water, but in reality, when you introduce foreign ions into your electrolyte, which sometimes can do some good thing, but mostly they will do something bad to your catalyst. And it can also introduce significant chlorine reaction, for example, when we do seawater splitting. And also most of the catalyst is designed for a specific pH value, but actually when you use in the device, it's completely different. In the microenvironment, local pH will vary significantly from your optimum pH value. And also there are bundle issues which can block your active surface. So all this type of water electrolyzer, they are actually under sort of it's a hot research area, and but I just want to emphasize that water electrolyzer is actually the cornerstone technology for hydrogen economy, and this technology is only valid for hydrogen economy if we use the renewable energy. And compared to traditional way like steam forming to prepare hydrogen, water electrolyzer offer the simplest way to produce high purity hydrogen. And today I will mostly talk about the alkaline electrolyzer and using one basically a sample material which is based on nickel and iron. So nickel iron has been popularly used for water electrolysis, particularly for OER reactions. But it's actually first known as a problem. So when Thomas Edison invented his nickel iron battery in 1901, the battery works in a way that you basically have an iron plate and nickel plate and dumped into an electrolyte, which is KOH. What he quickly noticed that when his positive plate has some iron impurity, sometimes there's a gas evolution inside the battery, and the battery fill very quickly. That's the first time people know actually iron and nickel work together can decompose water very rapidly. We can understand this better now by, for example, using this volcano plot where we can see the intrinsic activity as function of the metal OH bond strengths. none of the nickel or iron are good catalysts for OER. However, when they are combined together, they actually sort of have a optimum bond strength for OH, not too strong, not too weak, give us the best OER performance. So back in 2015, we actually introduced this work, and we use a very simple methods to prepare nickel iron onto a highly porous electrode substrate electrodes, which is nickel foam. So we use actually a nickel foam as substrate and do the electrode deposition in a nitrate-containing solution. So nitrate can be reduced and to locally generate OH, hydroxide ions, which can then react with nickel and iron, form a hydroxide coating onto the porous nickel foam substrate. We found that it's extremely thin nano sheets of nickel iron formed on the nickel foam substrate. So overall, we have a freestanding electrode with very high surface area and a very good mass transport property. So the electrode had very extraordinary performance and give us a very low onset potential around 200 millivolts, and which is the lowest overpotential reported at the time to deliver the OER at different overpotentials. But more importantly, what we found that is the electrode perform very well at large current densities. For example, at 500 milliamp per square centimeter, we have an overpotential only of 240 millivolts. So we contribute this high performance to the high intrinsic activity of the nickel iron itself, but also the large surface area and also the excellent transport properties. Particularly at these large current densities, we get a good transport of the reactants to the electrode surface, but also the gas bubble generated can be quickly released from the electrode. So after that, we're looking for strategies to further improve the activity of nickel iron. For example, Sean, who was a master student at the time in my group, who actually introduced this simple engineering approach to enhance the surface area. So basically, before depositing the nickel iron directly onto nickel foam, he added in another layer of vertical line nickel oxide nanoflake. And then on top of that surface, we then deposit our nickel iron nanosheet. And then we get an enormously enhanced surface area as well as the activity. And Yibing, who was a postdoc in my group and now I think is a professor in Southwest Jiaotong University in China, he was looking to change the surface property of the nickel iron. The approach he did was after depositing of the nickel iron hydroxide, he did a phosphorylation process and partially convert some of the surface into nickel iron phosphate. Phosphate is super hydrophilic, which gives us a very hydrophilic surface, which can promote the gas bubble release and also improve the OER performance. And Majid, and he was looking to approach to defect engineering. He was just did a simple post-treatment of the nickel iron electrode and put them in the reducing environment and generate some oxygen vacancy, and we also get improved OER performance. And Shen, also a research fellow in my group, who was now a professor in the Nanjing University of Science and Technology, who first invented this 2D nickel iron morph and used that directly as a OER electrodes. So all this approach, we have tried to improve the nickel iron for OER. And more recently, we are also looking to introduce another metal into nickel iron, particularly in the high valence metal like vanadium, chromium, tungsten, manganese, molybdenum, all those different particular high valence metals, in order to lower the oxidation state and also the energy barrier for the oxidation transition of the 3D metals like nickel oxidation, which is usually the thermodynamic limiting step for the OER. So I will use nickel iron as an example to explain some other progress in this area. So Xin used the simple electrodeposition methods. Basically, he just added chromium inside the electrodeposition bath, and then he got a nickel iron chromium adage coating on his nickel foam substrate. And then we use that electrode for doing OER. And what we immediately noticed that the nickel iron's chromium electrode appear as a lighter color compared to the nickel iron under the same applied potential. We know that higher oxidation state of nickel usually give us a dark color. So that gives us the impression that directly nickel actually during the OER maintain a relatively lower oxidation state. And then the OER performance showed clearly a synergistic effect. After adding chromium, we get improved OER performance. When we look at this pre-oxidation peak here, that is actually often attributed to the oxidation of nickel 2+ to higher oxidation state. What we noticed that there was a delay in the oxidation peak for the nickel iron chromium. So just adding chromium actually adjusts the redox chemistry of the surface as well. So we know actually there are 4 active phases of nickel hydroxide responsible for OER, and usually the beta phase nickel oxy hydroxide is the more active phase for OER, where nickel has a relatively lower oxidation state. Well, in the gamma phase, it has a much higher higher oxidation phase, and the beta phase nickel oxy hydroxide usually formed at higher potentials. So from this, the pre-peak shift, we can have a immediate sort of impression that actually we are forming beta phase nickel oxy hydroxide with a lower oxidation stage for the nickel. Fortunately, this could be picked up by Raman. So we used a simple Raman cell to do this in experimental. So what we use is using a spring-printed electrode, which is commercially available, and then we add a drop of the QH electrolyte, and then we immerse the Raman lens. So the laser hit the sample, and we can collect the signal. And we can run the polarization curve. We can still see on the surface of the working electrode, we can get enhanced OER performance compared to nickel iron. So we can actually say, for example, in the nickel iron case, there are 2 peaks, characteristic peak corresponding to beta phase and the gamma phase of nickel oxy hydroxide, and we can see with the applied potential, the nickel iron catalyst start to evolve this beta phase, nickel oxy hydroxide, and it has a stronger peak compared to the beta phase. In comparison, when we introduce chromium into the system, we notice that actually when we apply the potential, the chromium, the beta phase become the dominant phase in the nickel iron chromium system. And experimental the X-ray absorption near edge spectroscopy can basically we can find actually the iron actually remain the oxidation state remain unchanged in the nickel iron chromium, but there's a clearly sort of decrease in the nickel oxidation state compared to nickel iron. And then we use X-ray. We use the exhaust to understand better the activity, how the catalytic reactions distribute between the three metals. And what we can find out there is with nickel iron, when we apply potential, there's a decrease of the nickel-iron bond and both the nickel oxygen and also the iron oxygen. But compared to the second shell peak, actually iron has a small weaker peak, which suggests there's a more disordered structure on the iron, around the iron, and iron is more likely to be the active sites. So there has been a debate for many years around about the nickel iron, which is the active sites. Some people think it's iron, some people think it's nickel, and our results provide evidence that iron is more likely to be the active sites. So in the chromium case, when we introduce the chromium, basically there was when we apply a potential, we don't really see significant change in the nickel and iron, but we saw a significant decrease of the chromium oxygen bond, suggesting the stronger chromium oxygen bond which is the active site. And we also did some DFT calculation to which support actually chromium can be more active sites for OER at the nickel iron chromium system. We further extend this concept to other metals. For example, in this study, we extend that into nickel, iron, molybdenum for OER, and we can form this amorphous nanowire structure. And we also observe the improved OER performance as well as the shift of the pre-oxidation peak of nickel. Again, the Raman, operator Raman suggests clearly the beta phase nickel oxide hydroxide is the dominant phase during this catalyst, using this catalyst for OER. So another advantage we found with nickel molybdenum iron is that it also reduced the gas bubble over potential. So gas bubble is actually quite big problem in water electrolysis. The gas bubble is hydrophobic. It can absorb on the solid surface, block your active sites, introduce ohmic resistance, but also Faraday resistance. It blocks the mass transport of your electrolyte, and also can cause significant deactivation of the catalyst by migration, aggregation, or simply physical loss of the catalyst. So by introducing the molybdenum into the nickel iron system, we actually can tune the surface wetting property of the electrode significantly. We can see from nickel iron to nickel iron molybdenum, we actually get a super wetting electrode surface. So with the help of from Chiang, using their advanced microscope, we were able to sort of record this gas bubble evolution dynamics in a sort of, let me see if I can play this. So this is a typical nickel iron electrode where we apply a constant current of 500 milliampere square centimeter. You can see actually the gas bubble evolution is very big gas bubble evolved on the electrode surface and detached very slowly. So that's consider nickel iron is a very efficient catalyst, but we see quite significant gas bubble attachment on the electrode surface. But in comparison, when we have our nickel iron molybdenum, we can also see actually the gas bubble evolution is a lot stronger. The gas bubble is a lot smaller, but actually happening at a much detachment happening at a much faster rate. I have to emphasize the two video actually happen on the same current density. That means same amount of gas is produced. But with the molybdenum modified one, the gas evolution, the gas bubble is a lot smaller and faster. But we noticed one problem is in the optical recording, which is actually the current, probably the only available method to really monitor this gas behavior. But there's lots of limitations for this optical recording. For example, we can't really see much with a high current density where the bubble evolution is very strong. And also there's a lack of information on early stage nucleation and growth because due to the resolution of the microscope, you can only see until it grows to certain size. And also you see a gas bubble, you don't know whether it's attached to the electrode surface, affect your current or not. But more importantly, optical imaging requires the cell has to be transparent. But in reality, the cell is made of metal. So we need other approach to or complementary methods to monitor the gas bubble behavior. So we've introduced this operational impedance microscopy methods to monitor the gas bubble dynamics. So the fundamental principle is very simple. So we know the ohmic resistance of electrode surface is inversely proportional to the electrode surface area, right? So when you have a bigger bubble on the electrode surface, block the surface area, we have a higher resistance. So it can simply be described by this equation. And C here represent a coefficient for your cell, which can include your electrolyte used, your electrode material, geometry, the distance between electrode, all the other factors. And then we can record the EIS as a single frequency at a high frequency, for example, 10 kilohertz, where the other the other EIS component, for example, the phase relaxation or the Faraday charge transfer resistance, all those factors are removed. So we get a higher sensitivity by monitoring the resistance change. So using the nickel, iron, molybdenum as example, what we can see here, using nickel and iron, we can see all this very sort of noisy current. So here we don't really care about the actual value of the resistance, but really the fluctuation of the resistance. Those are actually caused by the gas bubbles. In comparison, actually, with the nickel, iron, molybdenum one, we see a very smooth curve. We can do a simple Fourier transform where we can actually have a sort of a mapping of the gas bubble evolution dynamics on the electrode over a certain period of time. So for example, with nickel, iron, molybdenum system, we see about two characteristic peaks, which suggesting the gas bubble has more uniform size and the release is also a lot faster. In comparison, we can see here in nickel iron case, we have a lot more peaks, which are suggesting there's a large population of gas bubble of different size releasing at different time. Okay, I talk about the OER. I want to quickly talk about the HER as well, particularly the alkaline HER. The alkaline HER, there's an additional step involved, which is the water dissociation, which actually involves more intermediates competing for the active sites. Therefore, the activity of the HER in alkaline is a lot slower than the lactic acid. To solve that problem, we need active catalyst with multiple active sites or active sites with multi-functionality. Again, with nickel iron is usually considered as a good OER catalyst, but it's usually not HER catalyst. So in this study, we actually show a catalyst, nickel iron catalyst, which can actually highly active for OER, for HER as well. So what we have here is making a particle, genus nanoparticle using a micelle-based synthesis, and we can have a catalyst which has a distinct different phase of crystal structure as well as conductivity. So what we have here, we actually end up with a catalyst with a nickel, metal, and also oxide, iron oxide phase. We can see from the EDAX mapping, we can actually form numerous stable nano interface, and where the HER is supposed to happen. And particularly when we see from this EDAX line scan, we can actually see the distribution of the nickel and iron. We did a range of calculation to confirm there's no nickel oxide in the system, and also there's a performance sort of so we have a sort of a metallic nickel and also the nickel iron phase in the nickel iron catalyst. And then the catalyst exhibit very good HER activity. What we can have here is also almost approach to the platinum for HER. And for comparison, we also prepared the nickel iron nanoparticle, have a fixed physical mixing of the both. What we can see here, the activity is much lower. We also made the nickel iron alloy, and also found the activity is much lower. So which suggests the nickel and the iron oxide interface is very unique for the HER performance. We can also see that with conventional nickel iron based electrode, when you do HER, you often see this reduction peak of iron, but in our catalyst, we don't really see that peak, suggesting those peaks, the active sites are actually not in situ form, but it's already on the catalyst when the reaction starts. And we could also say, actually, with OER, we can actually also, the catalyst also have significant OER performance, which is expected as for nickel and iron. And what we see here is actually, I want to bring your attention to the pre-oxidation peak. With other catalysts like nickel iron LDH or other electrode, you also see that pre-oxidation peak. But with our catalyst, that peak disappears. Again, that suggests actually the active site for the OER actually is not in situ form. It's already there when the reaction starts. So we have actually active sites at the interface for both OER and HER. So we did the DFT calculation to help us to understand that. And from here, what we can see, actually, the interface does produce optimum sort of free energy for both HER and OGR to happen. So I won't really go into the details for that. So one of the problem in the water electrolyzer is the stability. So what I want to say here is that most of our catalysts, tested catalysts, we are testing under a stable conditions. But in reality, water electrolyzer is often you have to shut down and start it and start up. So actually, there's a reverse current developed at that process, caused significant corrosion reactions. And we actually first introduced this reversible water electrolysis catalyst 7 years ago. We reported nickel, cobalt, iron catalyst. We failed patent, but we published that about 2 years ago in EcoMat. That's our first EcoMat paper. So we also test this nickel iron HER catalyst for the reversible water electrolysis condition. What we did there is we mimic the shutdown and startup process of the electrolyzer. Basically, switch the polarity of your working anode and the cathode during the electrolysis. What we found actually is the quite stable performance of the catalyst for this sort of intermittent conditions. So the message there is, if you have a catalyst with reversible physicochemical state, that they more likely will have a very stable water electrolysis performance. So I want to quickly summarize what we have shown today here. So I have shown you a range of strategies we have been used to improve the earth bonding catalyst for alkaline electrolyzer particularly. And the synergic interaction between metals are it's a very powerful source to improve for looking for new catalysts. And development of a Mendel technique is very important to understand those complex systems, and also not just only for the catalyst, but also for the gas bubble evolution. And stability is a crucial factor and for any real world application. For example, under the real intermittent conditions. And lastly, I want to quickly share some of our commercialization process. We have tried to commercialize some of our catalysts and bring that really into industry. So what I've shown here is some of our catalysts from the sort of atomic level design to really fabricate that in a very big scale. There's a lot of challenge there. We really have to think about, what method do we use to make those materials, not just design them. So there's quite a big difference when you move from lab scale synthesis to the industrial level fabrication. So catalyst, a good catalyst not necessarily mean you have a good electrolyzer. So there's when you scale up the catalyst, put them in the electrolyzer, the story is often different. So we've been trying to design our own electrolyzer from this lab scale stack to the bigger one, and also try to apply for this monster electrolyzers. That's also, besides the electrolyzer itself, there's actually a range of system built around the electrolyzer, like electrolyte circulation or gas separation. There's lots of room to improve in order to get a higher hydrogen production and reduce the cost. We built actually the first hydrogen production and refilling station in Shenzhen, China in 2016. And has been in operation. And we have built about 5 electrolyte refilling stations now in mostly in Shandong province. There's also other projects we are trying to link that to wind power and also solar power for hydrogen production. Here are some summary of some other lessons or we learned from those commercial sort of activities. So from the catalyst point of view, anode usually is not a big problem for alkaline electrolyzer, but the cathode actually is more problematic, particularly for the HER and using a non-precious metal, and acidic one, OER is more problematic. So we need a synthesis methods which can be scalable really in the industry conditions. And then stability is crucial in terms of for the real applications. So we have really tested the catalyst in the industrial conditions, for example, in high loading current density and highly concentrated electrolyte temperature extra. So all those requires sort of standardized testing protocol need to be developed for the field. And again, the gas bubble is a problem. And also there's the range of device and system development that need to be developed. So there's a lot of room for us to improve the water electrolysis technology and to bring down the cost of the hydrogen. Okay, so this is the group, and this I'm just a messenger here. These are the real heroes, and we are also generally supported by the government funding agency and also industry. And thank you all for your attention.
Thank you very much. Wonderful talk. It is very impressive, and not only fundamental research but also the industrial electrolyzer for water splitting. Very impressive. So I see a few questions from the webinar. The first one is that the audience is quite curious about the interface between the catalyst and electrolytes. I have noticed that one of your excellent work is engineering the hydrophilicity of the three-phase interface. Dr. Yibin's words, as I recall. Do you have any suggestion on this sort of interface modification, except for the hydrophilicity engineering?
Yep. So the example we show here is to tune the hydrophobicity and hydrophilicity of the electrode surface, and we use a phosphate salt to anion to do that. And so the interface design is actually quite crucial, and surface wetting is just one of them, and also I mean, this is a very general question, right? I mean, the interface design, from the catalytic effect point of view, you want your catalyst to be the surface area to be very large, and your electrolyte gets a very good diffusion to the active sites without being blocked by, for example, by gas bubble. Yeah, I mean, we change in EV's work. We basically change the surface composition of the catalyst, but you can also change the surface morphology, which can also affect the surface, for example, hydrophilicity as well, but also the electron transfer between your active site and the electrolyte. So there's a range of sort of scenario to explore.
And also, I see the second question about the surface reconstruction of the OER catalyst. As you mentioned in the water splitting electrocatalyst, the electrocatalyst always with surface reconstruction, especially for the hydroxide formation during OER process. So how to the catalyst converted into HER's benefits for HER reaction? If you use one catalyst not only for OER but also for HER, is it reversible, and how to realize that?
So I think let's the last work I introduced, right? Yep. So that's one of the problem with the normal OER catalyst, because the reconstruction of the active phase is in situ form, then there's a reconstruction of the surface, and then the stability is often a problem. But in this catalyst, what we have here is actually the interface. Actually, it's a stable interface, and there's no change of the interface during the OER and HER, and they provide different active sites for both OER and HER. Therefore, if we have a catalyst like this one, which the property is reversible, and then we can have a very robust sort of electrolyzer using this catalyst. But I completely agree. That's a very big challenge for the fields, and particularly for the if you want the active site to be the change to be reversible. But most time it's not the case. Yeah.
Great. And the last question was about industry application of OER process. You know, most of the industry water splitting happen at high temperature in strong alkali or strong acid condition. So how about your application of this process, and how about the durability of the catalyst?
Yep, it's a good question. So, okay, so some of the catalyst that has been commercialized that can actually sustain those conditions, which I won't disclose here. But many of the catalysts, including the standard nickel iron oxygen hydroxide, which is regarded as a benchmark for OER. In our experiment, what we found actually, it's actually not stable, particularly under the industrial conditions. We found actually temperature play an important role, and also the concentration of the electrolyte, and those two are the we found actually but those two are actually not often applied when we test the catalyst, in particular temperature. So it's a big, I mean, not necessarily the changes because of the chemical change. Sometimes there's also a mechanical change, because, for example, when you have this catalyst running at a high current density, high temperature, and it will generate lots of heat, right? And then the physical mechanic property of electrode is quite different. That often also lead to the activation of electrode. So different from the fuel cell field where people normally test the catalyst in a real device, but in water electrolyzer, we don't really usually do that. There's a reason for that. But that's what I sort of thinking. The field needs a more standardized testing protocol to mimic those conditions.
Oh, great. So the final one I just got a few minutes ago. So about the characterization of electrocatalysis at working condition. So if one interested in the absorption or surface reconstruction, so is there any special parameter or some rule to describe that? And how to rational design of the stable electrocatalyst under working condition?
Okay, again, this is a very big question. So I think the first part of the question was about in situ detection of the intermediate. Is that right? Yeah.
First one, you mean?
The first part of the question, I saw there was two parts of the question.
First about if one interested in the absorption and surface reconstruction, is there some rule or parameter to describe the working electrocatalyst for the absorption and the surface reconstruction? So do you are you interested in like the over potential or some signal can be detected in suit?
Yeah. So yeah, I think to understand the mechanism, it's important to develop in situ technology to capture those intermediates in order to understand the reaction mechanism, and then we can sort of design the catalyst to with higher efficiency, and therefore the optimal technology, which I showed only some example here, are very important. And what is the second part question?
The second part was about how to rational design of a stable electrocatalyst.
Yeah. So stability again is a big issue. So it depends on the material, right? So there's a range of material we can use for both OER and HER. Some material which has high activity, usually, I mean, for example, amorphous one it's give you higher activity, but they are usually less stable. So I believe eventually this is a balance between performance and stability. So what I want to say here is that most of the current study is focusing on the activity, but I feel it's crucial to bring the stability into consideration as well, for the sake of the real world application.
Okay, thank you. Thank you very much for your wonderful talk. And also I think the answer to those questions are very insightful, and it can enlighten a lot of important work in this field. Many thanks for your wonderful webinar, Professor Chuan. And also thanks Professor Minhua for the previous talk. And finally, I'd like to thank all the team before the computer cell phones. And also we are looking forward to the coming webinar in the April. So thank you. We are finished now.
Thank you.
Thank you very much. Thank you. So I'll see you everybody next month probably.